Okay, so today, last time we went over the multiband, which is like the most common sequence we run at the MRI center, and all sort of the deep dive into all the weird things happening under there. And so today, what I'm going to talk about two completely different things. So the first one is quantitative T1, and I talked at the 8 a.m. session on Friday. I talked about sort of semi-quantitative methods, like where you would do a pre-scan through the body coil to get rid of the coil fall-offs, and then also looking at something you could divide T1 by T2. That would be a way of also doing the same thing, and then you could also do MP2 range, which was like sort of collect two case-based volumes and then sort of do some computations with them. And today I'm going to talk about another method that I was involved with, so I know this one well. And so this is doing two different flip angles, and then also trying to correct for the B1 inhomogeneities, and that has to do with when you do a transmit from the RF coil, different parts of the brain don't absorb the same amount of RF, and so you get different flip angles. So how could we possibly fix that? And then also at the same time, how could we estimate T2 star quantitatively? So that's the plan for today. So, and then the second part, is to talk about SpinEchoBOLD. Now, BOLD, and I'll go over what that means. That's what we use for functional MRI to monitor oxygen levels, basically. BOLD depends on T2 star, and so why would you want to do SpinEcho, which sort of fixes the star part of T2 star? But there's a reason that you might want to do it, kind of a complicated one, so we'll go over that second. So first, sort of quantitative T1 proton density, T2 star. So the problem, the basic problem we have is that if you do an image, like a gradient echo image, you get a complex signal out. But if we just take the amplitude of that and throw away the phase, which is typically what we do when we're making an image, then the equation that describes how bright the center of the echo is going to be, and that's the part that sort of most strongly controls the contrast of the image, you get this equation, the proton density, which we sometimes call A, and this is the one that you did on the first homework. So it's proton density times the sine of the flip angle times 1 minus E to the minus TR over T1, and that whole thing over 1 minus the cosine of the flip angle times E to the minus TR over T1, and then that whole thing times E to the minus time of echo over T2. So that was that first equation for gradient echo in the steady state incoherent. So that was like where we're doing this spoiling. So that so we do a whole bunch of very rapid flips, and we assume that we're in a steady state, and then we try to get rid of the magnetization. So the incoherent. So that's the equation for incoherent steady state gradient echo. So the problem with this, which you can see, is a whole bunch of numbers on this side. You only got one number on this side, one real number, because you took the amplitude of the image, and you've got the flip angle is in there. There's TR, there's TE, there's T1. It's kind of a whole mess, and so you just get one thing back. And if we want to figure out like what is the T1, well, there's a lot of other variables in there, and so that's really the point of quantitative MRI is to actually get a real T1 number out instead of just a weighted image with arbitrary numbers in it. And so, there was, I looked at the video last year and there was an aside. So what does that equation look like? Well, that equation kind of looks like, something like this. If you plot out that equation as a function of the flip angle, so this is the flip angle that way, and this is the S amplitude that way. You get something that sort of looks like that. And another worthwhile equation which is useful in the lab is what is the maximum of that guy? And so the maximum of that guy is, that's called the Ernst angle. That's E for Ernst, one of the early nuclear magnetic resonance guys. And so the Ernst angle is cosine minus, the inverse cosine just means the angle whose cosine is that of E to the minus TR over T1. And so what is that useful for? Well, we always want more signal, and so what is the flip angle that gives us the biggest signal? And how might you use this? An example might be if you're doing functional MRI. Functional MRI is a gradient echo sequence, and it's in the steady state because you're doing it a bunch of times. And if you start to go faster, like we can do with multiband, then you start to run into a problem of maybe the T1 hasn't recovered. So if you do an RF pulse every second, then the T1 won't necessarily have recovered. So you'll be in this steady state situation where you need to find the maximum of this equation. So what is the flip angle that you would want to use? So normally you would use a 90 because a 90 will give you the most signal, but as you start to go faster and get into the steady state, you're going to start killing your signal. And so if you do a TR, like a new volume of a functional MRI scan every second, you need to actually sort of figure out what the flip angle is that's going to give you the biggest signal, and it's less. It's less than 90, might be like 60, something like that. So that's actually a small useful equation. So I kind of just sort of stuck that in there. It's because it's related to the maximum of this guy. But now let's look at this one. That's kind of a mess. And so the thing I'm talking about, this original derivation came from this paper by Helms. It's in the readings if you want to look at it. Helms et al. 2008. But what you can do is simplify that equation. And so this is, it's kind of above my pay grade for, the actual math analysis. But if you look at some of the basic assumptions here, so if we assume that the TR is much longer than T1, and in the case of a fast gradient echo in the steady state spoiled, the TR is only like 7 milliseconds or something, and T1 is like 2 or 3 seconds or something. And so that's certainly true. And so what we can do is we can do a linear approximation. And if you look at a signal like this that's starting here and then falling off very rapidly, right at the very beginning, it's kind of straight. And so you could sort of say like, well, why don't we just like sort of approximate that first part with a line? And that's much simpler than this exponential. But there's another kind of simplification you can do. There's something called a Taylor series. And a Taylor series is basically go to a point in some function and calculate all the derivatives. And what is the point of that? Well, it's just trying to figure out like where is it likely to go? Where is it likely to go next? But when people decompose something into a a series of derivatives like that, they almost always do it to throw away all the higher derivatives and just keep the first one. And what's an example of that? Like because we have sines and cosines, so what does a cosine look like? It looks like that. So what if we start here? What's the derivative there of the cosine at 0? Well, it's 0 because there's no change. And so there's some higher derivatives, but we just throw those out and just say, let's just sort of concentrate on the first derivative, and that's going to sort of tell us, where things go next. And so I didn't go over all the math of how you would do that, but if you do that, what you can get is another equation for this. Looks completely different, but it's linear. So this is approximately equal to that same thing up there, or the amplitude of that complex signal, is equal to the amplitude times just the angle, no sign there, and then times the TR over T1 over the angle squared, no cosine again, over 2 plus TR over T1, no exponential. Now, not being a mathematician, when I looked at this equation, I said, that sure doesn't look anything like that other one. But it's a linear equation. And so the idea is, the overall idea of what we're going to try to do here is we'll do two different flip angles and get two equations. And then after temporarily just throwing that guy out, we'll have two equations and two unknowns. So we'll have proton density, this thing here, and then T1. So we have just two unknowns. We got rid of all the exponentials and cosines and complicated mess. So we have two linear equations for that, and then we can simultaneously solve those linear equations for T1 and proton density. And so basically the plan of the paper is, here's a complicated thing. We'll make this one that looks almost exactly like it, but it's linear. And then we'll take two different flip angles and then solve for T1 and proton density. And then we'll say secondarily how we can actually estimate the T2 star. Sorry, this is a mistake. That's supposed to be T2 star up there, not T2. So the first amazing thing, just take this equation, just go into MATLAB and take these two equations, plug them into MATLAB and plot them. And if you do that, it's unbelievable. So here's the first equation, the real one. And then if you plot that one, it looks completely different. What do you get? You get something, it's just perfectly on top of it. And then it starts to you get out here and it starts to be off by a little bit, like less than 1% off here. And then it gets a little worse as time goes on. But it's pretty amazing, math. Yeah, I should have taken more when I was younger. So it's virtually copies that more complicated function. Okay, so if we then just solve for, T1, so what do we get? So we get T1, estimate. That's our estimate of T1 is equal to 2 times the TR times our signal from one flip angle divided by, should I get the right numbers in here? Yeah, divided by the flip angle. So that's the signal that we got from flip angle 1 plus the signal we got from flip angle 2 divided by flip angle 2. And that whole thing is over the signal 2 times flip angle 2 minus signal 1 times flip angle 1. So now we have a real T1 number. It's not just it's no longer just a arbitrary T1 weighted number. And you could do the same thing for, A equals proton density estimated equals, what's that one? So there was a mistake in the original paper, but it's corrected here. So it's the signal pixel brightness of one flip angle times the pixel brightness of another flip angle times the same thing, or this is alpha 2. Let's make sure we get that right. Alpha 2 divided by alpha 1 minus alpha 1 divided by alpha 2. That whole mess over signal 2 times alpha 2 minus signal 1 times alpha 1. So same thing. And so now we have two, I'll just call this proton density estimated. PD estimated. That's A. Okay, so now we can actually sort of solve for the proton density and the T1, as long as we have two scans. So we have to do two scans. So the downside of this, like I mentioned when I was talking last Friday, the downside of this is you've always got to do another scan, because one scan just has too many variables on the right side of it, and only one output number. So we got to get at least two scans. In this case, we're going to do two scans, and we're going to do multiple echoes to fix this guy, and then we're going to do another two scans. Now, the trick is always to make sure that somehow we can do this in not too much longer than we were doing before, just to get the weighted scan, so that somebody doesn't have to be in the magnet forever. And so a lot of the issues are how can we sort of shrink this down to make it sort of practical. So let's start with. Let me make sure I don't go too far over to the right here, because we need another pulse sequence on this side. So let's start off with the gradient echo sequence. So this is the gradient echo steady state incoherent sequence. So we assume that we're in the steady state, so we've been doing this for a while, and then we just do an alpha pulse. This is just a regular 3D gradient echo. So here's the Z, Y, X, and signal coming out. So we do an alpha pulse. It's a 3D, and so we'll select a whole slab there. That's slab select. But it's also, partition, the second phasing code direction, slab select. And then we do a whole bunch of phasing codes on the second phasing code directions. That means do this whole thing for all those different settings. And then we also have to do it for all these different settings of the real phasing code. So, it's like if that's 256, then we have to do this 64K times total repeated. So that one's, that's the phasing code direction. And then we go to the left of K space, and then go across K space. So that's what we would normally do if we were doing a fast gradient echo. And if we look at signal coming out, so there'll be a FID here, which we ignore, and then right here there'll be our gradient echo. But initially we threw this guy out, but how could we estimate that guy? So what we could do is just do some more echoes. Kind of like what we did with echoplanar imaging, except now we're not doing any blips. So the blips kind of move you up in k-space so that you do multiple different lines of k-space. But here we could just record the same line of k-space over and over. So we got one echo there. We could go to the, so we went, what this gradient did is we started at the left side of k-space, and we went across k-space and to the right edge, and now we reverse the gradient and go across all the way to the left edge, just like we would do with echoplanar, and then get another echo, and then a third echo, and a fourth echo, and a fifth echo, and a sixth echo, seventh, and an eighth echo. And now we're back at the left side of k-space. And so why would we do that? And so it's kind of, it's like, and then we have to do some spoil. So we'll just put spoil here, because we're in the incoherent state. I won't draw that in, so spoil. You could spoil with the RF, or spoil with an extra gradient. And so here's another alpha. But why would we do that? So what that's going to do is that will make, at each of these points as you go across the center of k-space for any given setting of the phase encode, the second phase encode and the first phase encode, you'll end up with a whole bunch of echoes. And so what will happen is that guy will make another echo here, and there'll be another echo here, another echo here, 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 here. And so you'll see a whole train of echoes all going through the same part of k-space. And what could we do with that? Well, what we could do is we could try to fit an exponential to that. And so what's the point of that is we want to basically fit like an e to the minus t over t2 star to that. And so it's this. So we could just, so what would happen? We would get a bunch of slightly noisy signals like that fell off from our 8 echoes, and then we would just try to fit a curve to that. And so then that would allow us to try to estimate this guy, that T2 star, all at the same time. So now we would have enough data to try to estimate our T2 star in addition. So, and as opposed to just immediately spoiling, we could just go back and forth at whatever place of k-space, 3D k-space we were. Okay, so what? But the question is, what do we use for this guy? Because this guy is the amplitude of the signal, but now we got 8 echoes. So you could just average them all. That's one straightforward way. So just average all these echoes. That's good because you're getting even more data. And so you could basically take the average of all those echoes for 2 different flip angles. So the idea is we would do flip 1, and then separately collect another scan with a different flip angle. So we have to do two different scans, 2 different complete 3D scans. And so now we have those 2 numbers to put into this equation so we can calculate the proton density or the quantitative T1. But now there's a problem of the flip angle. And remember, the flip angle wasn't the flip angle wasn't what we said it was. And why was that? That was because as we go to higher and higher Teslas, the wavelength starts to get smaller. So at 1.5 T, wavelength's like a meter, and that, when you do that to the head, it's pretty uniform, not too many hot spots. I always say just like the microwave. The microwave is 2.4 gigahertz, so that's 2,400 megahertz instead of like 100 megahertz for our 3 Tesla. So it's 20 times the frequency, hence 20 times the energy, but also the wavelength gets much smaller in the microwave, and so then you get little hot spots in your TV dinner. And so the hot spots in the MRI are not nearly as hot. They're only like 30% hotter than the surrounding. So because the wavelength isn't that small yet, but it's still big enough that if you're trying to, calculate, say, the difference between gray and white matter, those two curves are pretty similar to each other. And so if you're off by 30%, that's enough to actually flip the contrast. So it's a big enough effect that will actually change the contrast of the image. And so we would like to estimate it. And so how should we estimate it? Well, last time we talked about echo volume imaging. So there was echoplanar imaging where you select a slice and then you record all the k-space data after just one RF pulse. That's what echoplanar imaging is. And then you select another slice, do the same thing. In echo volume imaging, what you do instead is you excite the entire volume, and then you just collect one plane of k-space. So what does that mean? So remember, each point in k-space comes from the entire head, so a plane of k-space isn't a slice. What it is, a plane of k-space is basically all the kx and ky data points for one kz. So a plane of k-space is like for a single z direction spatial frequency, a certain spatial frequency of spin flips, spin twists in the z direction, collect all the kx and ky. So it's not a slice, really. It's something that's coming from the entire head. And now it happens to be equivalent to the number of slices. So if you collect, say, 64 different kz planes, that will reconstruct into 64 pixels in the z direction, but they're not really slices in the sense you're not selecting a slice. You're instead exciting the entire volume, so every single point in that 3D k-space comes from the entire head. So that's an echo volume type scan, but then not only that, so we have to do sort of echo volume imaging, but then we're going to also do stimulated echo and also a spin echo. So both of those, because we need multiple equations in order to calculate what the actual flip angle is. And so this pulse sequence is a little more complicated than the other one. Hopefully I've got enough room here. Let's see. So we'll go across. Should be enough. So 2, 3, 4, 5. Okay, so this is, the signal coming out. This is the readout gradient and the phasing code and the slice, second phasing code, and RF in. So in this case, we do an RF pulse, and we'll call this guy alpha. It doesn't have to be 90. And then we'll do our slab select. So that's this guy's a slab. So the whole volume. Slab select. Similar to this one, where we're exciting the entire volume. And then, but we need a spin echo. and how do we do a spin echo with a gradient echo EPI? So the way we do that is we just do another pulse. So here's another pulse. So this guy is 2 alpha. So we talked about the special case of 90 and 180. So if you do a 90 and 180, that would be, alpha and 2 alpha. So that's a possibility. But we're trying to figure out these lower flip angles. And so why are we doing that 2 alpha business? Well, remember when we had the equation for our spin echo, the equation for the spin echo was some constant times sine cubed of the flip angle, assuming that we have this situation where the second RF pulse is twice. Then it simplifies to sine cubed. It's more complicated if you just have arbitrary pulse flips. But if the second flip is twice the first, then you get this simpler sine cubed times e to the minus tr over t1. So that's the amplitude of the, no, it's not over t2, right? So that's the amplitude of the spin echo. So amplitude of the spin echo. But there's several things in there, and so if we do a stimulated echo in addition by doing another RF pulse, then we could have a second equation, and with that second equation, then we could actually solve for what the flip angle actually was, because it's going to be 20 or 30% different in different parts of the brain. So then we have to get a stimulated echo. But let's first sort of finish up. So at this point, you can sort of arbitrarily say in the middle of this there was a FID which we didn't record, and then this guy is going to cause, if it's not 180, it's going to cause another FID which we're also going to ignore, and then this amount of time afterwards, like right here, we're going to get our spin echo. So this is, this is our tau, and then here's tau again, and that's when all the phases come back into alignment, and we get a spin echo over here. But now we're going to do like an EPI readout, a gradient echo EPI readout of that spin echo. And so how does that work? That works, we have to, do some 3D phase encoding here. So we have to sort of pick a bunch of one of those, one of the above, and then now we're going to do our EPI-like readout. So go to the left. This is the Y one. So go to the bottom part of K-space, and then go to the left side of K-space. That's what that is. And then we'll do a EPI readout, and so there's going to be a whole bunch of back and forths here, like back and forth, across that whole echo. So there'll be like 64, back and forths all crunched together, and then there's a bunch of blips here. There's all the blips. Those are blips because we have to sort of advance through Y K-space because we're collecting all the data for one plane of K-space for a given setting of the Z spatial frequency. So this sets the Z spatial frequency, and then we collect all the possible combinations of X and Y spatial frequencies. Here are 64,000 combinations. So these guys are blips, and this is EPI going back and forth. Okay, so that's all good. So now we've got spin echo 1 and 2. But if we want to make a stimulated echo, how do we do that? Well, we got to do another RF pulse. And so where is that RF pulse? We'll put it right over here. And this is another alpha pulse, our third one. So this is, you know, it's our third one. And so what will that do? That will just make another FID, which we ignore. And then we will look for the stimulated echo. And where's the stimulated echo? Well, the stimulated echo is going to be that amount of time, tau, after the third pulse. And so if we take that amount of time here, right at that point, so that's tau again after the third pulse, then what's going to happen if we, you know, go down here, there'll be a stimulated echo, nice big stimulated echo. So that one that's, you know, stimulated echo that is 1, 2, and 3. It requires three pulses for that to happen. And then there'll be another spin echo because there'll be, you know, there was this, you know, this amount of time later over here, there's going to be another spin echo, which we're just going to throw out. So there'll be another spin echo here. This is, you know, spin echo 2, 3. So you can sort of see what the problem is. There's like too many echoes. Spin echo 2, 2, 3, and we'll just ignore that guy. But the stimulated echo, what we will do for the stimulated echo is just do another set of, you know, you can see there's a lot of combinations you have to do. So another set of this one. We can pick the same one again that we did this first time, and then in this case we're going to have to we're probably at the right side of K-space, so maybe we have to go to the left side of K-space like that, and then start doing all our readouts. So we do a whole bunch of readouts, just like we were doing EPI during that echo, and then we got another bunch of blips. So we're being pretty efficient. We're collecting, you know, a lot of data quickly. So all we have to do is, and the other thing about this, we don't have to do like extremely high resolution. So then we get 2 complete 3-dimensional K-spaces, that one of which has the spin echo and the other one has the stimulated echo. And what's the point of doing this? So the point of doing this is the amplitude of the stimulated echo is a different equation. So, and that equation is k divided by 2 sine cubed again, cubed of the flip angle, times e to the minus tr over t2, and then times e to the minus tm. I didn't define that one yet, over t1. Because remember we said there was like, we stored some magnetization in the longitudinal plane, and so it decayed with a t1 constant instead of t2. So what was the tm? So sometimes, just to simplify things, we can call this distance tm, time of mixing. That's what it stands for. So that's sort of, you know, mixing during the funky stimulated echo. So that's that amount of time. But now we have 2 equations, and so now we can solve for the flip angle. And so our flip angle estimated is going to equal the inverse cosine, you know, angle whose cosine is our signal of our stimulated echo times e to the minus tm over t1, just divided by the amplitude of the spin echo. So we got rid of that t2 business in there. So so that's our final answer. So now we've got a way to estimate what the actual flip angle was, which is varying all over the place. And if you want to look up this, there's a lot of different. None of these ideas are new. So these people have been trying to estimate the actual quantitative T1 for 40 years, 50 years. Okay, so it's so there's many ones, but this one, if you want to look it up in the readings, this is Giroux and Klose, 2006. Just to sort of see what it looks like, in an actual paper, in the literature. So now we've got a way to estimate the spin echo, but we got to do this twice because there's two different flip angles. And so that's why, we do it for one flip angle and then do yet another one for another flip angle. The advantage of this is that we don't have to do a very high resolution. So this is our B1 map. So what we're trying to do is get a 3D volume of what is the actual flip angle that you did. And so what do we need that for? Well, we need that for like here's one flip angle and here's the other flip angle, and so we've got to go down and sort of get those out of here in order to substitute that into the equation to put the real flip angle that we actually did into our equation. So this B1 map, it can be. So the B1 map can be pretty low res, so that means it doesn't take very long. It takes about a minute or so, an extra minute to collect this data. That's not too bad. And this one over here, so this one over here is our main scan. We'll say main scans. So there's two of these, and these guys are high res. So because the flip angle doesn't change, the hot spots aren't too hot, and so the flip angle doesn't change too rapidly, and so we can do a low resolution one here, and then subsample that into our high resolution scan in order to calculate the T1 proton density, and then the T2 star estimated for this one. So that's our T2 star estimated. To go with the T1 estimated and proton density estimated. So then we have a really good quantitative estimate of what these values actually are that are real numbers. They can compare across scanners, or you could compare. You could scan somebody a year later and then say their T1 has changed, or their proton density has changed, or their T2 star has changed. So obviously, it's extra scans, and so the problem is how can we get it done fast enough? So what will probably happen in the future is that this will all be packaged into a single scan. So it's like I said last year, it's all about de-skilling the scanner operator. So the scanner operator won't really know what's going on. They just press this button like quantitative T1, T2 star proton density, and everything comes out. And so if you built this whole thing into a single scan sequence that lasted about 10 minutes, that's a practical amount of time that you could scan somebody, and then you would end up with real numbers instead of just weighted numbers. So as usual, it starts off easy, and then it sort of gets harder and harder. But this is just one of many different ways of trying to estimate these real numbers from your scan that are actual quantitative numbers that you can compare across time, and you can compare across scanners. Particularly across scanners, because all these different scanners have slightly different setups and different brightnesses that come back. Okay, so why all the effort to do this? One of the reasons was, if you look at cortical areas don't, the white matter and the gray matter vary quite a bit. There's like 5 or 10% difference between the gray matter and the white matter. So if you're just trying to find the boundary between the gray and the white matter, or how much gray matter there is, something like that, that's relatively straightforward. But if you're trying to figure out different cortical areas, some cortical areas vary. So like some areas might have more myelin in the cortex itself, which changes the T1, than some other cortical area. So this cortical area might have more myelin. That difference is only, at best, like 3% or 4%, but a lot of cortical areas only vary by like 1%. And so that's why we really need a quantitative number in order to be able to pick up these small differences that distinguish different cortical areas. So this would be like one cortical area here. Cortical area, gray matter, with a lot of myelin, which means brighter in a T2 scan, in a T1 scan. Brighter in T1. So that one would be slightly brighter, but just like 2% brighter or something like that. But that's enough to actually recognize where that cortical area is in a particular person. So that was actually the motivation why I got involved with this, because I was trying to sort of divide up the cortex into different areas based on how much myelin they had in the gray matter, because that's something that people had done for 100 years, trying to distinguish different cortical areas by seeing how myelinated they were. So that's the actual motivation for all the mess. Okay, so any questions about quantitative T1, proton density, T2 star? You got an equation with a whole bunch of numbers on the right, and so we have to somehow collect multiple data points in order to sort of resolve that, in order to have enough information to actually calculate what the T1 or the T2 star or the proton density actually is. So this is proton density here. I just put the A in there because that's what was in the paper. Okay, sort of clear. Okay, let's erase this whole mess and talk about SpinEchoBOLD. So first, what is BOLD? So BOLD, I haven't really talked about it yet, but BOLD is blood oxygen level dependent contrast. And why? So what's so big about it? Well, for many years I would go to the neuroscience meeting and I would see, in the 80s and the 90s, early 90s, and I would listen to the MRI guys talking about their latest experiments on whether they had seen any signal related to brain activity. And back in that day, one of the best ways, or the only practical ways of recording brain activity was with PET. But PET involves actually injecting somebody with a radioactive tracer that comes out of an accelerator down in the basement, and it's made very quickly and injected quickly. And there's some possible damage from injecting a radioactive tracer. And so I remember year after year I'd see the MRI guys talks, and you'd say like, no, still not working. And then one day in 1992, 93, somebody gave a talk, and all the people were there, like me, said, "Oops, it's working now." So that's when I really got into MRI, because suddenly you could record, brain activity without any radioactive tracer, so you could do it again and again. So that's BOLD. So BOLD which is, blood oxygen dependent, oxygen level dependent. There we go. Scan. So how does this work? So if we have a blood vessel, so you've got hemoglobin in here, and hemoglobin is what's the iron in it is what's holding on to the oxygen. So oxy hemoglobin. Now the neurons are our neurons are sitting out here. So if you look at how the oxygen gets out, how does it get out? Well, it has to diffuse out. And how can it diffuse out? It can only diffuse out if there's more of it in the blood vessel. So it's kind of counterintuitive, but if this guy is calling out for oxygen, so how does this guy call out for oxygen? It somehow talks to the glia, and the glia go down, and then they have a nitric oxide mediated opening of the capillaries, and so these capillaries, little tiny capillaries, will just sort of pop open like in less than a second as soon as these guys cry out for oxygen. So how do they cry out for oxygen? Well, some activity happens, some ions change, the glia pick up that, and then somehow they signal by touching these little capillaries. So this guy's a capillary to open up. But remember, the places that are using oxygen, so at first you would think the places that are using oxygen should have less oxygen because they used it. But it's actually the reverse. The places that are using oxygen have more oxygen because you needed an excess of oxygen in here to cause the diffusion to occur. So there's actually more oxygen in the areas that are using more oxygen. Kind of counterintuitive. But where does the signal come from? We haven't really mentioned, where does the signal come from? So it comes from the fact that deoxyhemoglobin is paramagnetic. So the deoxyhemoglobin is paramagnetic. And so what does that do? That causes a B0 defect, a static B0. Now, static is static in terms of, atoms. It causes a static B0 defect. And what does a static B0 defect do? Well, it's a T2 star. It's the star part of T2 star. It causes the magnetic field to be disturbed statically, which dephases things and kills the signal. So the bottom line is deoxyhemoglobin kills the signal by dephasing it. But because excess O2, where it's used, that means less deoxy where O2 is used. And so that means less signal kill. There's a lot of double negatives here. Less signal kill, end result brighter. So that's, after a number of years, that's basically how people finally sort of rationalized why it got brighter when there's some brain activity. So the deoxyhemoglobin kills the signal. But there's less of deoxyhemoglobin where there's oxygen in use, and so it turns a little brighter. Not a lot, a couple percent brighter. So that's the basic rationale for why you want to use gradient echo, because this is a T2 star effect, and so that's why you want gradient echo. And a standard EPI scan, EPI, gradient echo, is typically what we use. So why would we want to use spin echo? So this is an argument. If you want to read this argument, you can look up Rick Buxton. He retired, but he was at UCSD. And so this combines. It combines several things. So it combines, BOLD, which is this blood oxygenation level, but then we have to sort of talk about spin echo. Normally, if you did spin echo, you'd figure that would cancel static B0 offsets, fix them, rephase them. And so you'd expect that to kill the signal. And in general, that's what you see. So if you just try a spin echo scan, a spin echo EPI scan instead of a regular EPI scan, your BOLD signal will mostly go away. But why would you want to do that? You still might want to do it anyway. And so this has to do with talking about diffusion of spins, not oxygen, diffusion of spins. And then, the T2 star effect, which is these static offsets. So what's the argument? So the argument is if we go around a big blood vessel. So here's a big blood vessel. Now the big blood vessel has a lot of deoxyhemoglobin in it, and it can get magnetized. And when you magnetize the blood vessel, you'll get sort of a magnetic, kind of like a magnetic dipole coming out of this magnetized blood vessel. And I'm just sort of trying to draw, these are supposed to be sort of like positive and negative parts of the field. So if you have a magnetized blood vessel, you'll have some sort of pattern like that of positive and magnetic field vectors outside of that large blood vessel. So this guy is a large blood vessel. Now, we don't actually care too much about large blood vessels or spins that are right outside blood vessels. So here's a spin out here that we're recording from. So why is that? Well, if you look at what the cortex looks like, so if I draw a little chunk of the cortex like this, it's got these blood vessels, running over the top. So there's a big blood vessel running over the top, but that's carrying oxygenated blood somewhere else. And then what happens is they break up into these tiny little arterioles that sort of go through the cortex. So this is the gray matter, cortex here. And that's the actual thing we want to record. We don't want to sort of record something that is outside of a big blood vessel. We want to record these little. We want to record spins that are like right here, just right next to the place where the action is going on. And so one of the reasons why you might want to do SpinEchoBOLD is to cancel this signal. And so how does SpinEchoBOLD cancel this signal? So let's take another case. Here's a little arterial or a little capillary, and that's also going to get magnetized. And so here's the little magnetic field dipole that's sort of generated around this small vessel. So this guy is a small magnetized blood vessel. This is a large magnetized blood vessel. So now let's consider diffusion, because spins diffuse around. So here's a spin out here outside this large magnitude blood vessel, and it's just in Brownian motion. It's just sort of zigging around like that. is randomly. We'll talk more about diffusion recording later. And then here's a spin here, and this guy is diffusing the same amount. This guy's diffusing the same amount, same distance. And so what happens is that this guy will not, because the magnetic field changes around this large blood vessel are relatively smooth, this guy will be more or less in the same magnetic field position as it diffuses around, and so in that case, spin echo kills. So spin echo kills this signal. Over here, what's going to happen is it's going to diffuse into different magnetic sort of surroundings because it's diffusing the same physical distance as the last one did, as it did over there. Here, this distance is the same, on average. But it's going to go into different magnetic field positions. So spin echo will still kill here, but it kills less. And so we're more likely to get a signal that actually comes from the place in the cortex where the activity actually was. And if you actually look at, now, why don't people do this all the time? Well, they tried it at the very beginning, and they said, it just completely kills our signal because, it's a T2 star effect. But if you go up to a very high field, like 7 Tesla, you have a lot more signal because 7 Tesla, uses more energetic photons. So you got enough signal to sort of, you can burn up some signal by doing spin echo. And if you do that and look at a regular gradient echo sequence, and look at it in the cortex at high resolution, where is the signal? It's up toward the top here. It's up in these vessels, coming from these vessels. But those vessels are not so good because they're sort of, there's some oxygenated blood in there, but it's going somewhere else. It's not being used right there. And so you get kind of a sloppy signal. Whereas if you look at what the signal is, so this is our gradient echo signal as a function of depth, and it's mostly up in these big vessels, so you're kind of recording blood vessels rather than the actual place, down in the cortex where it's being used. Now, if you do spin echo, what happens is you see something that's more like what's actually going on in the cortex. You see some, there's a lot of really big cells in layer 5, and so those cells will show up. And so you actually see SpinEchoBOLD. So you actually see, now the signal's less, but it's a better signal. And in a place where you have a map, like in V1, for example, V1, where you can, there's a retinal map, you can actually, and if you do something like stimulate a small part of the retina and look at what the signal comes out, you'll see it's much more localized and much more accurate representation of the map than the gradient echo. So that's an example of the sort of the complex argumentation. You can see it's a combination of diffusion of spins and T2 star, how that sort of interacts with it, and spin echo sort of selectively kills the signal coming from big vessels and shows you something closer to the actual places that are active. Now, why doesn't everybody do this? Well, it kills the signal, and so 98% of functional MRI is still, or 99% of it is still gradient echo. But it's good to know, it's kind of a sloppy signal. It's not really, where the activity oxygen is being used. It's more sort of localized to the surface, to these large vessels on the surface. Okay, so this was kind of a rough lecture, but that's SpinEchoBOLD, so why you might want to do that. And at very high fields, even at 3T, it works somewhat at 3T also, but at very high fields, especially 7T, where you can make much smaller voxels and you can burn some signal, that's one advantage of using SpinEchoBOLD, which otherwise would be kind of a weird thing because it kills the signal, which it still does. Okay. Sarah went over any questions about SpinEchoBOLD. So, and in terms of the pulse sequence, it's very similar. You just do, instead of a 90 and then do the echo planar readout, you just do a 90, 180, and then do the echo planar readout. Okay. Any final questions or all good? Okay, we'll see you on Wednesday.